Yeah, good morning, one and all. So, what we are discussing? We are discussing about unit number 6, non-linear pharmacokinetics, right? Non-linear pharmacokinetics. So, what are the major important things we need to cover? Under this non-linear pharmacokinetics, you are going to read the causes of non-linearity, and then next one is Michaelis Menten equation. Only two parts it is having. Under this Michaelis Menten equation, you are going to read about three different situations. Are you remember this? Three different situations. What are those? Km is equals to C, Km is greater than less than C, Km is greater than C. So these are the three situations we already read. And then you are going to estimate the Km and Vmax by three different methods, right? What are those three different methods? First one is Linear Burke plot, and the second one is Hansen Wolf plot, and the third one is Augustine plot. So the sixth unit is most important and very simple unit it is. So damn sure question is Michaelis-Menten equation and causes of nonlinearity also. So under causes of nonlinearity, you are going to read about absorption, distribution, metabolism and excretion, saturation mechanisms with a clear examples. So this is of causes of nonlinearity what we learned, right? And under Michaelis-Menten equations, you are going to learn about these three situations, and here you will get three different equations. And then for estimation of Km and Vmax, we have studied about Linear-Burke plot, Hansen-Wolf plot and Augustine plot. So here this Michaelis-Menten equation will explains us regarding Km and Vmax only. Km is Michaelis-Menten constant, and then Vmax is the theoretical maximum of the rate process. So these two parameters are very important. So for that reason we are going to estimate these two parameters by using different kinds of methods. Okay, those are Linear Burke plot, Hans Wolf and Augustine. So these three plots will explains you to calculate Km and Vmax at normal concentrations. Okay, at normal concentrations. And one more important thing here, you need to remember, you can estimate this Vmax and Km at steady state concentrations also. Steady state concentration. This is the last topic in the sixth unit. So this Linear-Burke plot, Hansen-Wolf plot and Augustine's plot are useful to estimate the Km and Vmax at all the concentrations. And this Km and Vmax can be estimated at steady state concentrations also by using three different methods here also. See, what are those? Calculation of Km and Vmax at steady state concentration. Just remember ma, whenever they will ask to write you about the Michaelis-Menten equation, you have to write along with the steady state concentration also. Three situations you have to write, and estimation of Km and Vmax also you have to write. And the third part is calculation of Km and Vmax at steady state concentration is also you have to write. So these three will includes you Michaelis-Menten equation. Definitely they will give for more marks. So that's why this is also one of the part under Michaelis-Menten equation. So the calculation of Km and Vmax at steady state concentration. So when you are going to calculate this Km and Vmax at steady state, how you will obtain this steady state? You already know about IV infusion. So what do you mean by IV infusion? The drug release will takes place very slowly. slowly. The drug release will takes place slowly. So for that reason, the drug will be released up to prolonged periods of time. So in this case, you need to consider the dosing rate. Why? Because the drug will be released up to prolonged period. It will not be released rapidly. Right? So in case of IV bolus, your drug will be released rapidly. So in that situations, you cannot exactly calculate the dosing rate. So in case of IV infusion, the drug will be transported at a constant rate. So here the drug, in the sense, the drug will follows non-linear kinetics only. Just remember that. So here we are talking about non-linear kinetics, right? So if your drug will be administered, that drug will be transported into our body through a constant rate when you have given such drug through IV infusion. That's what, or in a multiple dosage regimen. So what do you mean by multiple dosage regimen? Single dose means either it may be 10 or 20 or 30 mg. So in case of multiple dosage regimen, in a single day, you need to give multiple doses. That is 10, 20, 30. Together, you need to give in single day, multiple dose. Okay, single day you have to give multiple doses. This is what the multiple dosage regimen. So in this situation also, your drug will be attain some steady state. And here you need to get two situations for obtaining the steady state drug concentration. What are the situations? One situation is when you administer the drug through the IV infusion. In that IV infusion, the drug will be transported at a constant rate. There we will get a steady state concentration. And one more situation, or in a multiple dosage regimen, we will get a steady state concentration. So when the drug will be following nonlinear pharmacokinetics, there is a calculation of Km and Vmax at the steady state concentration. If your drug is administered through IV infusion or through a multiple dosage regimen, the steady state concentration will be given in terms of dosing rate. Why? Because in case of IV infusion and in case of multiple dosage regimen, we are able to see the dosing rate differences. So you are going to use different doses at different rates. So that's why instead of calculating your dc by dt, what do you mean by dc by dt? This is a rate. This is a rate of the process. Instead of calculating this rate of the process, here you are going to calculate the dosing rate. So you just remember that whenever you are going to calculate Km and Vmax at steady state concentration, you have to use dosing rates, because the dosing rate will be varied in case of IV infusion or in case of multiple dosage regimen. Simple thing. Okay, so that's why the equation will becomes dr, that is dosing rate, is equals, what is this? CSS, steady state plasma drug concentration, and this is the total clearance. This is the equation you have to remember. So the dosing rate is equals the steady state. SS is representing you steady state. So steady state plasma drug concentration, and this is of T is total, CL is clearance, total body clearance. So the dosing rate will gives you about the steady state and the total body clearance. So the next equation will, if the steady state is reached, then the dosing rate is equals the rate of decline in the plasma drug concentration. So what is that statement? Suppose if you are plotting a graph between the plasma drug concentration versus the time profile, your graph will be like this. Then it will be declining. So here it will reach a steady state. So in this steady state, your plasma drug concentrations will be high. See, the plasma drug concentration is higher. After reaching steady state, the plasma drug concentration is declining. Here, the drug concentration is declining. So, at this point, your dosing rate DR is equals the rate of decline in plasma drug concentration. Once your drug will reach this steady state, the DR is equals rate of declining in plasma drug concentration. Only up to this mark it is increasing. After that it is declining or decreasing. So then your if the steady state is reached, then the dosing rate is equals the rate of decline in the plasma drug concentration. When if the decline occurs due to single capacity limited process. Single capacity limited is nothing but it is absolutely following your Michaelis-Menten equation. So what it is saying your Michaelis-Menten equation? The drugs which will follow single capacity limited mechanisms, that is nothing but one compartment open model we are assumed, right? So if your drug will follow single capacity limited process, and when the steady state will be reached, so the dosing rate is equals to rate of decline in the plasma drug concentration, your equation will becomes. So what is our Michaelis-Menten equation? DC, this is capital C and this is minus, right? dC by dt is equals Vmax into C divided by Km plus C. This is our standard Michaelis-Menten equation, right? So here at steady state, when the dosing rate is equals to the rate of declining in the plasma drug concentration, this equation will becomes. Here you are not going to calculate rate of a process. Here you are calculating the dosing rate, so that the equation will becomes Vmax into CSS divided by Km plus CSS. So why here I am writing CSS instead of C? Here we are talking about steady state plasma drug concentration. So that's why instead of writing directly plasma drug concentration, you can write steady state plasma drug concentration. See, the equation is same. dr is equals to Vmax into CSS divided by Km plus CSS. So first, before writing this equation, everyone has to write the standard Michaelis-Menten equation like this. Then you can able to get this equation. So instead of talking about this rate of process, we are talking about dosing rates. Why? Because of the variation in the dosing rates, we need to get steady state of plasma drug concentration. That's why instead of writing rate of processes, we are writing dosing rates. So this is what the equation number 2. So the next one is from a plot of CSS versus DR. So when you plot steady state plasma drug concentration versus dosing rate. So your dosing rate can be either of mg per hour or mg per day. mg per hour or mg per day. That means suppose 10 mg per 6th hour, then again 10 mg per 8 hour, like that. This is per mg per hour. Here we are representing hours, and mg per day is total 100 mg per day. So that is meaning of this total 100 mg you can take in single day. This is what the dose per 100 mg per day, and this is what the doses per hours. So this is the same. That is dosing rates. Here when you take the plot on x-axis, you can take, here it is very light, so once again I will draw. This is dosing rate and this is plasma drug concentration at steady state. When you plot the graph like this, you can get a curve like this. This is looking like a hockey stick. See here, this is looking like a hockey stick, and this will joins you the this axis. And then when you extrapolate this axis, you will get Vmax by 2. Why we are getting Vmax by 2? Here this is representing you Vmax, that is theoretical maximum. But here we are getting half of the Vmax. That's why Vmax by 2. And then this is of your maximum responses, right? Which responses? Maximum theoretical responses. That's why it is Vmax. So the total you can calculate as Vmax. We are getting just half of the Vmax. Then we have to write Vmax by 2. And this is Vmax, this is Vmax by 2. And here this is a constant at the steady state. That is nothing but Km. Km is Michaelis-Menten constant. So when we are plotting the relationship between the dosing rates and steady state plasma drug concentration, we will get a shape of hockey stick, okay, which is obtained, that will be shown in this figure. And then we are able to get the slope of the slope of this graph is Vmax by 2, and then the theoretical maximum is Vmax. The slope is Vmax by 2, and then the y-intercept is Vmax. So here this is the relationship between the dosing rate and the steady state plasma drug concentration when it is following nonlinear pharmacokinetics. When you have to give this dosage form through intravenous infusion or multiple dosage regimen. So the graph will be like this. So here we are taking the dosing rates in mg per hour or mg per day. So this is the basic concept of this steady state plasma drug calculation of this Vmax and Km. So then the methods, what are the methods you need to use to determine this Km and Vmax at the steady state? So what are the methods? Same like previous thing, you have three different kinds of methods. See, there are three methods which are used to define Km and Vmax at steady state, that is CSS, with appreciable accuracy. So the first one is linear Burke plot, and the second one is direct linear plot, and the third one is graphical method. So here you are going to describe about these three methods which are used to define or to calculate or to estimate this Km and Vmax at the steady states. Okay, so first one, the linear Burke plot. So the reciprocal of equation number 2. So what is the equation number 2? Equation number 2 is dr is equals to Vmax into CSS divided by Km plus CSS. You just write equation 2. This is equation 2, right? So the reciprocal of this equation 2, we will get, reciprocal means 1 by. So it is looking like this. 1 by dr is equals to Km CSS. Km plus CSS, Km by Vmax into CSS. See, Km is extracted from here, Vmax into CSS plus 1 by Vmax. So this is the reciprocal of this equation number 2. So you will get the linear Burke plot. So how the plot will be? See here, this plot is not mentioned in your textbooks. So if you can consider to plot 1 by dr on x-axis against 1 by CSS on y-axis, a straight line will be obtained like this. See here. So what is our equation ma here? So basic equation is dr is equals to Vmax into CSS by Km plus CSS. Okay, by learning these equations, you can plot a graph. Without learning the equation, you cannot plot the graph. So the reciprocal of this equation is our linear Burke plot. So how you will get the reciprocal? Km Km divided by Vmax into CSS plus 1 by Vmax. This is of the reciprocal of linear Burke plot. So when you plot this equation on the graph between 1 by dr. Here on x-axis you can take 1 by dr dosing rate, and here on y-axis 1 by css steady state plasma drug concentration. 1 by 1 by, why 1 by? This is the reciprocal of that equation, so that's why. Okay, so then you will get a straight line like this. It is a straight line, so you have to calculate the slope. So for that reason you are extending the graph. So this y-axis will beyond this x-axis. You can extend the graph this y-axis beyond the x-axis. You can get the dotted lined slope, that is km by Vmax. This is the slope km by Vmax. See, slope is km by Vmax. And then you are getting intercept as 1 by Vmax. This is the intercept 1 by Vmax. What is intercept? Where the point joins the y-axis is called intercept. Here x and y both axes are joining this point. This is called intercept. This is a joining. So which intercept it is? Y intercept, because the x-axis point is joining y. So it is called y intercept. So 1 by Vmax is y intercept and slope is Km by Vmax. See how simple it is. First you can write the basic equations, then you can extrapolate them into reciprocal forms, then you can plot the graph. You will get one method, that is linear work plot, to estimate the Km and Vmax at the steady state plasma drug concentration. So this is the slope and this is the intercept. Okay. So the next method is direct linear plot. So for the estimation of Km and Vmax at the steady state concentration of a drug when you administered at different doses. Different means here it is one dose and here it is second dose. That's why here you are going to take two different dosing rates, that is dr1 and dr2. So if you are taking two different rates, definitely you will get two different steady states. That's why here CSS1 and CSS2. So how the plot will be? See, you just plot like this. First you can take the x-axis. In the middle of the x-axis you have a y-axis plot. See, in the middle of the x-axis you have a y-axis. So when you take the dr, on y-axis and CSS on x-axis, okay, here it is a 0 and here you can get some minus values, negative values, and here you have a positive values. Here minus values and here positive values. So when you plot like this, okay, between the x-axis you can plot the y-axis. So we are taking dosing rates on the y-axis and we are taking steady state plasma drug concentration on the x-axis with two different dosing rates. Those are dr1 and dr2 will appearing you like this. This is the important question, ma. That's why I am telling you two to three times. So just catch my points. So here the two dosing rates will be joining. See here, this is the plasma drug concentration 1 and this curve is the plasma drug concentration 2. So here at this is the dr1 and this is the dr2. At dosing rate 1, you can able to get steady state plasma drug concentration 1. At dosing rate 2, you can able to get CSS2, plasma drug concentration 2. So this is the dosing rate differences at two different rates. So then what about Vmax and Km, where they are? See, so this is the Vmax point. Here you can take this as Vmax point. Vmax is maximum theoretical yield, at which point we will get maximum theoretical yield, that will be considered as Vmax. So up to this Vmax, when you extrapolate the graph to touch this x-axis, you will get Km here. So this is the Km. Okay, this is the Vmax. So the graph is same like this graph, but this is very light to see. That's why I plotted once again. So you just adopt the concept clearly. So this direct linear plot is useful to estimate the Km and Vmax at the steady state plasmadrag concentration. When you take the drug at two different doses, those are DR1 and DR2, we can able to get two different steady state plasmadrag concentrations. So which gives us to calculate Vmax and Km as we have shown in this plot. So this is about the direct linear plot. And the third important one is graphical method. So this is a very simple method. It is also used to estimate the Km and Vmax at the steady state rate. Okay. So by derivating all these equations, first you can write our basic equation of steady state plasmadrag concentration, how you can calculate the dr. This is our equation number 2, basic equation. So first everyone has to write this equation. Dr is Vmax into CSS divided by Km plus CSS. So in the graphical method, you can rearrange the equation 2. See, you can rearrange. How you will rearrange this? You can take it out, this Vmax, then it will gives you minus. If you take this Vmax, it will gives you minus. Then Km, this is multiplied. Km into dr, then divided by CSS. See, it is a very simple equations. Your dr is like this. So then your dr is extracted is equals Km minus Km into dr by CSS. So this is of the fourth equation. This is of the fourth equation. Equation numbers are also important. And then this Km and Vmax can be estimated by simultaneous equations. Why we are telling us simultaneous equations? In this second method and third method, we are going to calculate the dosing, different dosing rates, that is DR1 and DR2. So for that reason, we can able to calculate this Vmax and Km from two different dosing intervals. So for that, DR1 is there and DR2 is there. So in case of DR1, how the equation will be? Vmax, okay, into DR1 and CSS also 1. It will becomes 1. Why? Because here we are going to calculate dosing rate 1. So then if it is will be a dosing rate 2, how the equation will be? Vmax minus Km into dr2 divided by CSS2. So instead of 1, it will become 2 because we are going to calculate dosing rate 2. So these are fifth and sixth equations. On solving above equation 5 and 6, on solving above these 5 and 6 equations, we will get Km is equals, see, how you are going to solving this? See ma'am, this is dr1, right? Vmax minus Km dr1 divided by CSS1. dr2 is equals Vmax minus Km dr2 divided by CSS2. So how you are going to solving this? So what is our aim here? We are going to estimate the Vmax and Km. So first you just take it out this Km. Km you just extract from this equation. So first you can able to write dr2 minus dr1. So divided by dr1. Where it is dr1 by CSS, you can write dr1 by CSS. You extracted Km already. So for that the equation will becomes dr1 by CSS 1 minus, here also same thing, dr2 by CSS 2. So this is the equation for estimating the Km and Vmax. Okay, we can get this fifth and sixth equations like this. So this is what your seventh equation. So here, for estimating the Km and Vmax, we are considering the dosing rates at different intervals. So we can able to get two different steady state plasma drug concentrations. So Dr1 is representing CSS1 and Dr2 is representing CSS2. And how the plot will be. See, graph is plotted by taking the Dr against Dr by CSS. Okay, so here you can take the Dr and here you can take the CSS. So you will get the slope like this. The slope is minus Km. This is the theoretical maximum. That is y-intercept. See, this is the plot of dr versus dr divided by CSS for determining the Km and Vmax. The Vmax is y-intercept and the slope is minus Km. These graphs are not at all cleared in your textbooks. Okay. By substituting the values of dr1, dr2, CSS1, CSS2, we get value of Km and from Km we found the value of Vmax at the steady state concentration. From the experimental observations, it shows that Km is much less variable than Vmax. See, here it is representing minus sign is indicating you this is a decreasing value, declining value, so it will be always less than this Vmax. So here it is not Vmax by 2, okay, here it is exactly Vmax. That means here we have a maximum theoretical rate process in this plot, that is direct plot. So this is what your methods of estimating Km and Vmax at the steady state plasma drug concentration. And what are the limitations? This is the last slide for this sixth unit. Limitations of Km and Vmax. It is estimated by one compartment system by a single capacity limited process. So what are the limitations? Limitations are also called as disadvantages, right? So more complex equations will result and the computed Km and Vmax will usually be larger. So here you can able to find out this Kmax and Vm, we are able to get more number of equations. So if it is difficult, if we will get more number of equations, definitely it is some difficulty. We will get this Km and Vmax derivations. So here this is the more complex equations will results you difficult for computing, that is comparing this Km and Vmax results. And the drug elimination is more than one capacity limited process. But here they are telling us about the drug is following only single capacity limited process, but based on this review of these equations we are knowing that the elimination is more than one capacity limited, so it is not a single capacity limited. That is also one drawback. And the drug is showing capacity limited at first order elimination process parallelly. So the drug is, if it is following single capacity limited, it is showing first order elimination process. So if it will following more than one capacity limited process, parallelly it is showing single capacity limited process also. And based on this capacity limited process, we can able to say that it will follows multiple compartment kinetics. Not it is not at all following this one compartment system. It is following multi-compartment kinetics. So the drugs with non-linear kinetics with therapeutic range yields is less predictable results. So it is not at all yielding a good predictable results. With this non-linear kinetics, we can able to get less predictable results. That means we are not able to get accurate results in the drug therapy and possess greater potential in precipitating the toxic effects. So this is the drawbacks of non-linear pharmacokinetics, and this is the very important in your exam point of view. You can able to focus Michaelis-Menten equation, okay, and then for this Michaelis-Menten equation, first you can write these three situations, then measurement of, then measurement of Km and Vmax by three different methods. This is at all plasma drug concentration levels. So Linevier-Burke plot, Hansen-Wolf plot, and Augustinson plot. And then you can able to learn measurement of Km and Vmax at steady state also, CSS. Here you have three different methods. Same Linevier-Burke plot, and then you have a direct plot and then graphical plot. So you have to remember that one thing, Linevier-Burke plot is always the reciprocal of the equation. This is a very simple method to remember. So here in case of measurement of Km and Vmax at normal concentrations, you can able to remember the Michaelis-Menten general equation. So for that, if you reciprocate this equation, you will get here the Linevier-Burke plot equation. So here instead of writing CSS, the equation is under steady state plasma drug concentration. And then this reciprocal of equation you can get this Linevier-Burke plot at this point. So this is all about Michaelis-Menten equation only. Don't get confused. Here you have 6 plots. So you have to plot all the 6 plots while writing in your exam point of view, and you must write the running notes for this class 6th unit. Okay, so that is the most important topic. From this slide I completed this 6th unit of non-linear pharmacokinetics.